Welcome to the deep dive. Today we're tackling something that sounds simple, but is actually a massive engineering challenge. Drilling a really, really long straight hole deep into a piece of material.
Exactly. You might think, drilling a hole, how hard can it be? But it gets incredibly tricky when that hole is deep relative to its width.
We're talking about when the depth is, say, 10 times more than the diameter, that LD ratio.
Yeah, that length to diameter ratio. Once you get past about 10 to 1, trying to do that on standard equipment, it's usually heading for disaster.
And not just a little bit wrong, right? We're talking like catastrophic failure, the drill bit wandering way off course.
Completely off center.
Yeah.
Because there's nothing supporting it deep inside the material.
And then the chips, the metal shavings, they clog up the drill's flutes.
They clog everything. And when that happens, your coolant can't get in. So the cutting edge gets super hot, runs dry, and bang, broken tool.
And a very expensive part suddenly becomes scrap. I can feel the pain.
It's this compounding error issue. Even a tiny wobble at the start becomes a huge deviation deep down. But, where standard machines fail, that's where specialized tech comes in. And that brings us to the deep hole drilling machine, the DHDM.
Okay, the DHDM, this isn't your average drill press then. These are purpose-built for those crazy LD ratios, over 10 to 1, sometimes even. What was it?
Sometimes up to 300 to 1. It's quite extreme.
300 times deeper than it is wide? Wow.
And they're essential because they take this incredibly risky, unreliable process and make it, precise, predictable even. You get amazing accuracy, great surface finish, often in just one shot.
So that's our mission for this deep dive. Figure out how these DHDMs pull off this magic trick. We need to look at the big challenges they overcome and the specific tech they use.
Right, so we're talking deep holes. It's fundamentally a control problem, isn't it? A standard machine just doesn't have the stiffness or the special tools needed. What are the, say, 3 key problems DHDMs are built to solve? Yeah, there are 3 main hurdles they absolutely have to clear, things that just stop conventional drilling dead. First, getting that hole perfectly straight and keeping it straight.
Okay, straightness, number 1.
Second, you have to get the chips out continuously. Forced chip evacuation, we call it.
Right, no stopping to clear chips.
And third, you need direct cooling and lubrication. Right at the cutting edge, deep inside the hole. All 3 have to work together perfectly.
Let's dig into that first one, straightness. On a standard drill, I'm picturing it bending, like trying to push a wet noodle through something hard.
That's actually a pretty good analogy. Standard drills just deflect. They follow the path of least resistance, and any tiny error at the start just gets magnified the deeper you go.
So how do DHDMs avoid that?
Well, first, the machine itself is built like a tank, ultra-rigid, to resist any vibration or bending. And critically, the tools themselves are designed to actively guide themselves straight. We'll get more into that, but it's key.
Okay, so rigidity and self-guiding tools. Now, hurdle number 2, getting those chips out. You mentioned forced evacuation. I remember seeing old-timers doing peck drilling.
Oh, peck drilling. Yeah, that's the standard, slow way. You drill a tiny bit, pull the drill all the way out to clear the chips, go back in, drill a bit more.
It sounds incredibly tedious.
It is. For a really deep hole, you could be doing that hundreds, maybe thousands of times. It takes forever and risks damaging the hole every time you re-enter.
So DHDMs just blast the chicks out.
Basically, yes. They use a high-pressure coolant system that continuously flushes the chips away from the cutting zone, right out of the hole. No stopping needed. It's a massive time saver.
Which brings us to hurdle 3, cooling. That high-pressure coolant is doing double duty then, clearing chips and managing heat. Why doesn't the usual flood coolant work here?
Flood coolant, where you just spray the outside, it's useless for deep holes. Imagine trying to cool the bottom of a hole that's, say, a meter deep and only 10 millimeters wide.
Yeah, the coolant wouldn't even get close to the cutting edge.
Exactly. Just hits the top surface. Deep inside, the cutting edge overheats, wears out fast, and ruins the whole surface finish. DHDMs inject a powerful targeted jet of coolant right where the cutting happens. It cools and lubricates effectively.
Okay, so solving those 3 straightness, chip removal, cooling means you can't just use a longer standard drill bit. You need totally different tools.
Completely different approach. And the choice between the 2 main specialized methods really comes down to the diameter of the hole you need. Both rely heavily on that high-pressure coolant, though.
What are the 2 methods?
They're gun drilling and BTA drilling.
Gun drilling. Sounds specific. Is that for like firearm barrels originally?
That's where the name comes from. Historically, yes.
Yeah.
It's generally used for the smaller diameter holes,
Hmm.
typically ranging from about 1 millimeter up to maybe 40 millimeters or so.
Okay, 1 to 40 mils, and that's when you need extreme precision.
Exactly. Think medical devices, fuel injector nozzles, really precise mold components. That's gun drilling territory.
So how does it work? How does it get coolant and chips out in those small holes?
It's quite ingenious. The gun drill tool usually has just a single cutting edge. Critically, it has a small hole running right down the center of its shaft.
Ah, an internal channel.
Yes. High-pressure coolant is pumped through that internal channel. It shoots out right at the cutting face, cools it, and then the force of the coolant blasts the chips back outside the tool along a V-shaped groove, or flute, on the tool's exterior.
So coolant goes in the middle, chips come out the side groove. Got it.
It's a very effective system for smaller diameters.
Okay, then what about BTA drilling? You said that's for larger holes.
Right. BTA stands for Boring and Trepanning Association. This method is typically used for diameters, say, above 20 millimeters, sometimes much larger.
And how does it handle the coolant and chips differently? If you're cutting a bigger hole, you're making a lot more chips.
You are. So BTA basically reverses the flow compared to gun drilling. Instead of coolant down the middle, high-pressure coolant is pumped around the outside of the drill tube, between the tube and the wall of the hole being drilled.
Okay, flooding the outside. Then where do the chips go?
They get flushed back through the hollow center of the BTA drill tube itself.
Ah. So chips come out the middle this time.
Correct. This internal chip evacuation is much more efficient for removing the larger volume of chips you get with bigger diameters. It allows for significantly faster drilling speeds, higher material removal rates.
Makes sense. Get the bulk out through the bigger central pipe. You mentioned tray panning in the name.
Yeah, sometimes BTA tools don't turn the whole diameter into chips. A tree panning tool cuts an annular groove, leaving a solid core in the middle, which can sometimes be removed separately or just falls out. It's even more efficient for really large, deep holes.
Interesting. Is there a variation too?
There is ejector drilling. It's sort of a modification of the BTA principle using a special double tube system. It allows you to get some of the benefits of BTA, like internal chip removal, but on machines that maybe aren't fully equipped for the high-pressure external coolant supply needed for true BTA.
Okay, so gun drilling for small, precise holes, BTA for larger, faster drilling, both using high-pressure coolant in clever ways.
Precisely. They're tailored solutions.
Which brings us back to that fundamental question. How do they stay so incredibly straight when the cutting edge is buried deep inside the part, totally out of sight? It seems almost impossible.
It does, doesn't it? But it's not one single thing. It's really a synergy, the machine, the process controls, and especially the tool design, all working together.
Let's talk more about that tool design. You said they're self-guiding. How does that actually work?
It's fascinating. Both gun drills and BTA tools aren't just cutting tools. They have specially designed non-cutting surfaces, little pads or bearing areas, built right into the head of the tool.
Okay, pads. What do they do?
As the tool cuts, the forces generated are carefully balanced by the cutting-edge geometry in these pads. They press against the newly cut cylindrical wall of the hole.
So they rub against the inside of the hole.
Exactly. But it's a controlled rubbing, almost like burnishing. It smooths the surface and, crucially, it creates a balanced pressure that forces the tool head to stay perfectly centered and aligned. It counteracts any tendency to wander off course.
So the tool actively uses the hole it's creating to steer itself straight. That's clever.
It's the core principle that allows for such extreme straightness.
Yeah.
But of course, that only works once the tool is properly engaged in the material.
Right. You can't just start it wobbling. How do you guarantee a perfect start?
You need a perfect entry. This is done using a very precise, hardened guide bushing. It's positioned right against the workpiece surface. The drill starts through this bushing, which provides rigid support and ensures it enters the material exactly on center and perfectly straight.
So the bushing gets it started right, and then the self-guiding pads take over once it's deep enough.
That's the process.
Yeah.
The bushing gives it that critical initial guidance until the tool has created enough of its own straight hole to stabilize itself.
Let's revisit the coolant system again, but thinking about accuracy now. You said it clears, chips, and cools, but does it help with precision too?
Oh, absolutely. It's critical for thermal stability. Think about the heat generated by cutting metal, especially for hours on end in a deep hole cycle.
Things would expand, right? The tool, the part.
Exactly. If the tool or the workpiece heats up significantly, it expands. even a tiny thermal expansion can change the diameter of the hole you're drilling. You might start drilling a 20 mm hole, but finish with one that's 20.05 millimeters at the bottom because everything got hot.
Ah, so the constant flow of coolant keeps everything at a stable temperature.
Yes, and often the coolant itself is temperature controlled. By preventing that thermal growth, the DHDM ensures the hole diameter stays incredibly consistent from top to bottom. It's another layer of a precision control.
And presumably, the machine itself has to be incredibly stable to support all this. No vibrations allowed.
Zero unwanted movement. DHDMs are built on extremely rigid, heavily damped bases. They use high-precision components like linear guides and ball screws to ensure smooth, accurate motion without any deflection, even with these long, heavy tools hanging way out.
Any other machine stability features?
Yeah, for long drilling cycles, heat can even build up in the machine's spindle bearings. So many DHDMs have active cooling systems, often circulating chilled oil, just for the spindle assembly itself to prevent any thermal distortion in the machine structure that could affect positioning accuracy.
Wow. So it's the rigid machine, the guide bushing, the self-guiding tool, and the thermally stable coolant system all working together.
It's a complete system approach.
And the results, what kind of precision are we actually talking about? Can we quantify it?
We certainly can. In terms of the hole diameter, you can achieve tolerances in the range of IT7 to IT11, which is, very precise for machining.
And the straightness. That's the really mind-bending part.
That's where it truly shines. Deviations can be as low as, say, zero point 0.5 millimeters over a depth of 1,000 millimeters. So half a millimeter drift over a meter deep, sometimes even better.
Less than a millimeter over a meter? That's almost perfectly straight. Unbelievable compared to what a standard drill could do.
Completely unattainable by conventional methods at those depths.
Okay, so these machines achieve the impossible. Where does this capability actually matter? Which industries need this kind of deep, straight hole?
Well, it's really any industry that needs components that are strong, light, efficient, and often involve moving fluids or require long, precise internal features. The demand comes from pushing engineering boundaries.
Can you give us some main sectors?
Sure, the big ones are definitely mold manufacturing, think injection molds, aerospace and defense, naturally. The automotive industry is a huge user. Energy, especially oil and gas exploration and extraction, and increasingly the medical device field.
Let's make that concrete. Molds. What kind of holes are needed there?
Primarily, really long cooling and heating channels. To control the temperature of an injection mold precisely, you need to circulate fluid through intricate, deep channels drilled deep inside the mold block. The straightness and placement are critical for part quality and fast cycle times. Also, ejector pinholes need to be very straight over long distances.
Okay, what about aerospace? I'm picturing landing gear.
Exactly. Hydraulic lines drilled directly through large structural components, like landing gear struts. Also, components for actuators, missile bodies, even firearm barrels require that extreme precision and straightness over depth.
Automotive. Where are they hiding in my car?
Deep inside the engine block and crankshaft, primarily. Think oil galleries, long, winding passages drilled to deliver lubrication precisely where it's needed. Also, in transmission components, fuel system parts. Anywhere you need controlled fluid flow deep within a metal part.
And medical. That sounds like very small, precise holes.
It often is. Cannulated surgical instruments are a prime example. Drills or reamers used in surgery that need a hollow center for guide wires, irrigation, or suction. Also, orthopedic implants like bone screws or rods often require precise internal features made by deep hole drilling.
So the common thread seems to be moving fluids deep inside a part or needing a long, straight mechanical bore.
That sums it up perfectly. Whether it's coolant, hydraulic fluid, lubricating oil, or even a guide wire, if you need a precise internal pathway deep within a solid component, a DHDM is often the only way to create it reliably and efficiently.
They really are essential then. Hidden, maybe, but critical.
Absolutely. They enable designs and functionalities that just wouldn't be possible otherwise. They are fundamental tools for a lot of modern high-performance manufacturing.
Okay, let's wrap this up. It's clear DHDMs are these highly specialized, almost invisible workhorses solving a really tough problem.
Yeah, using technologies like gun drilling and BTA drilling, they achieve levels of precision and efficiency in deep holes that standard machines just can't touch.
And here's something profound to think about. We talked about the precision, but that high-quality surface finish you mentioned, the one that comes right off the DHDM.
Right, the burnishing effect often leaves a very smooth finish.
That often means companies don't need to do other operations afterwards, like honing or reaming to get the final size and finish.
Exactly. It can eliminate entire steps in the manufacturing process.
Which translates to huge savings in time and money. So, and the next time you see any complex device where fluid has to move efficiently deep inside a solid part, maybe your car's engine, maybe a complex valve, maybe even a tool a surgeon uses, just remember the hidden world of the deep hole drilling machine. It's the technology that makes that precise internal universe possible, doing it incredibly straight, incredibly accurately, and often all in one efficient go.